Welcome back, dear students and parents who are watching this program. We are in the track of doing some questions of class 12 physics from the chapter current electricity. Some questions already we have done, and a few more we will discuss today as per the availability of time. One question I'll give you very fast, that is, if there is a wire of resistance 8R, okay, there is a wire of 8R resistance is 8R, okay, and it is bent into the form of a circle. What will be the effective resistance between the ends of the diameter? That's one question, okay. That is, see, this is stretched, the wire is bent into the form of a circle, and the question is, what will be the resistance between the ends of its diameter? You consider one diameter, so A and B, the ends of the diameter, and what will be the resistance between the ends of the diameter, and total resistance given is 8R. 8R is the total resistance, okay. What's the question? Once again, let me tell you the question. A wire of resistance 8R is bent into the form of a circle, okay. What will be the effective resistance between its diameter, okay. So this is the diameter and effective resistance. So this part is like, we are dividing the resistance 8R, diameter will divide the circle into two equal halves, no. So this part is 4R, this part is 4R, correct. So we can redraw this diagram as one resistance here 4R and second resistance also 4R, right. So 4R and 4R connected in parallel. So if remember a general point, if two resistors of equal values, if connected in parallel, what will be the effective resistance? The effective resistance of the combination will always be half of one of them, okay. That is, say for example, here 4R connected in parallel, so what will be the effective resistance? Will be 2R. So what will be the answer here? So the total resistance becomes 2R. That's the answer, final answer. So what's the question here? Once again, a wire of resistance 8R is bent into the form of a circle. What is the resistance between the ends of its diameter? So this is how you calculate. This is the answer. I hope all of you understood, right. So in this, remember one more question related to or similar to this one. I'll just show you that question as well before I show you another question on the screen. Now listen this. This is the question. A letter A, correct. The letter A is made from a uniform wire, and its resistance is, let's say, 2 ohms per centimeter. Okay, the resistance of the wire used for making the letter A is 2 ohms per centimeter, and the question is, we're going to find out the effective resistance between its ends, okay. And what else given is this is given as 60 degree, okay, and what else is this is, let's say, this is 2 centimeters, okay, this also 2 centimeters. It's all given like that. So 2 centimeters, this is 60 degree, means what? It should be an equilateral triangle, so this would be 2 centimeter. So this every segment is of the length 2 centimeters. Now what the question is now? Question is to find the effective resistance between these two. So once again, let me tell you the question in the construction. The letter A is made using a uniform wire of resistance 2 ohms per centimeter as shown in the diagram. Find the effective resistance between its ends. That's the question. So how to approach this question is, you can make out one thing. These two wires are connected, end to end. These two wires are connected end to end. That means they are connected in series. So I am going to redraw this diagram in the form of resistors. Alright, so this segment you can take it as a resistor. See, this is what I draw as one resistor, then it is another resistor is attached to it. See, these two I drew, and even this one is this, and here one more resistor. How about this part? This segment is nothing but connected in parallel to these two. See, this is how we redraw in the normal way, conventional way. Same diagram, okay. And what are the values? And it is given 2 ohms per centimeter. 1 centimeter 2 ohm. So what will be the resistance of one segment? One segment is 2 centimeters. No, 2 into 2. So 4 ohm is the resistance of each. 4 ohm, 4 ohm, 4 ohm. This is 4 ohm. This is also 4 ohm. Got it? That means now how do you find the effective resistance? Think of this part. See, these two resistors are in series. So 4 plus 4, 8 ohms is the resistance. Then next what? 8 ohm and 4 ohm in parallel. You know the equation R1 R2 by R1 plus R2, that equation you can use. 8 into 4 by 8 plus 4, 32 by 12. You can calculate the effective resistance of this in parallel. Once again let me tell you, 4 plus 4, 8. This 8 is in parallel with 4. Find the effective resistance. Then that is in series with this and this. That is 4 plus this whole thing plus 4. That will be the total resistance. I hope it is clear. Clear? So this is, all of you have seen the question. This is the question. This is how you have to reduce it, and further you can calculate the effective resistance. Alright, now I will show you another question which is asked in one of the board papers. Just have a look at the question. You can watch the screen. Look at the question. Calculate the steady current through a 2 ohm resistor. You observe the circuit very closely, but there is a mistake in the question. So there is only 2 resistors. The center wire is not there. I will redraw it over here on the board. Okay, 2.8. Have you seen the question, all of you? Okay. 2 microfarad, 2 ohms, 3 ohms, 6 volt. Okay, now look at the diagram. Now we can see the board. Okay. See, this is the question, and what you are going to find is calculate the steady current through 2 ohm resistor in the circuit shown. That is, how much is the current through this resistor? That is a question. How to find it out? We will make it in this way. Very first thing to understand is, when a capacitor is connected, capacitor is, in current electricity lesson, we haven't studied the case of circuits involving capacitor. Capacitor we have done in electrostatics lesson, the first unit. So here the capacitor, meaning what, it does not let the current flow through it. So it is blocking the flow of current. So what we can make out is there is nothing over here, means no current flowing through it. So we can simply take this out. Okay, so this part we don't need to consider. That is the important aspect to understand. Then if the remaining is there, then easy, so 3 and 2 in parallel. What will be the effective resistance 3 and 2 in parallel? Rp is equal to, what's the equation? R1 R2 by R1 plus R2. So that is 3 multiplied by 2 by 3 plus 2, right? 6 by 5, that means 1.2 ohms. Right? So 1.2 ohms is the resistance of this part, and what else? Along with that, this resistance also we should add. Series, correct? So this is 1.2 and this one is 2.8. So 1.2 plus 2.8 is how much? 4. Clear? So 4 ohm is the total resistance. And how about the total EMF? 6 volt. So what will be the total current then? Total current is total voltage divided by total resistance. Total resistance, how you get 4? That is 1.2 plus 2.8. So 6 by 4, that is 3 by 2 amperes. So 3 by 2 amperes is the current through the whole circuit. But again, see what's the question? Actual question is to calculate the current just through 2 ohms only. Current through 2 ohms. So, but to find the current through 2 ohm, we need to find out how much is the potential difference across 2 ohm. How to calculate potential difference across 2 ohm? This as a whole, how much is the resistance? We calculated, that is 1.2. Correct? 1.2 ohm is the total resistance. If you know the total resistance and you know the total current, we can find the total potential difference across this. So the potential difference between A and B, let me write it as VAB. Potential difference between A and B is what? The current, that is 3 by 2 multiplied by the total resistance, which is 1.2. Total resistance of the parallel combination. Okay, so 3 by 2 multiplied by 1.2. 1.2 and 2, when you cut, it will become 0.6 multiplied by 3. So it will become what? 1.8. So 1.8 volts is the PD across this parallel combination. So if you know what's the PD across this parallel combination, in a parallel combination PD is the same in both, correct? Everywhere potential difference is the same. So whatever PD we calculated over here 1.8 volt is the same in both. So what will be the case? What will be the current through this? Current is 1.8 divided by 2. Okay, so that means 0.9 amperes. 0.9 amperes is the current through 2 ohm resistance. Okay, the current is coming through this is through this 0.9 amperes. Is it clear? Okay. So now this is the picture. The question was, again have a look at the question. You see on the screen. Okay, you are given the diagram and you have to calculate the current just through 2 ohm resistor. Okay, so the question now you on the board. This is how you solve it. Okay, this is the diagram and this is how you calculate the effective resistance in parallel combination, and after that the PD we found out of parallel, then therefore current through 2 ohm resistance. Okay, that's the method. Clear? Now you can I will brief you something about potentiometer. You must be very much alert on learning in concepts of potentiometer. And potentiometer usually the most of you find little difficult in catching up or in cracking the questions of potentiometers. So I will brief you something about potentiometer. So listen the concept very carefully, after which we will do some questions based on potentiometer if time permits. Okay. Listen now. This is the high resistance wire we use in potentiometer. By the way, you might be remembering the potentiometer, how it looks like in the lab when you have seen potentiometer. You know, this is how a potentiometer looks like. You know, many wires, many high resistance wires there. You know, 10 meters or 8 meters wires we have. This is how normally this is how a potentiometer looks like. But in the numerical problems, when it is given, it will be given as a single wire. You know, AB is the high resistance wire, which is what is drawn like this. Okay. So this wire AB. Now this wire is connected to a cell of EMF, let's say E dash, and there may be a resistor R, resistance R. Okay, in this case what happens is this resistance it may be used to control current through the wire AB. So this circuit, when you draw like this is what they can call as the primary circuit. Okay, so a potentiometer circuit has two segments, primary circuit and secondary circuit. Okay, so here this is a cell, another cell of EMF E, and you may connect it to a galvanometer, and the other end of the galvanometer you can connect it to a jockey, jockey which can be moved through the wire AB. So the basic picture to understand carefully is, so just in simple terms I am explaining. To calculate potential gradient, so understand the term potential gradient. What do you mean by potential gradient? You know, usually we will use the letter phi to represent potential gradient. Potential gradient means, across this wire AB there develops a potential difference. That potential difference divided by its length will give you potential gradient. So in order to calculate potential gradient, what you should do is, you don't need to look at the secondary circuit, just see the primary circuit, this part. So using the value of the EMF, using the total resistance means it includes the high resistance over here as well as the resistance of the wire AB. So total EMF E dash divided by total resistance of the circuit will give you total current. Is it clear? That gives total current. That current, if you calculate, that multiplied by the resistance of the wire AB gives what? Potential difference across AB. Is that clear? Once again, the total EMF of the circuit, this I am talking about primary circuit, EMF divided by total resistance. Total resistance includes this as well as resistance of the wire AB will give you current. That current multiplied by the resistance of the wire AB gives what? Potential difference across the wire AB. Okay, potential difference divided by then its length, maybe length is 10 meters or 8 meters, so whatever potential difference you calculated divided by the length gives what? The potential gradient. That's a potential gradient. What's the importance of that is, generally we will write potential difference across AB divided by length of the wire AB. This gives the potential gradient. What's the importance of potential gradient? Now we think of this one. Potential gradient means how much potential difference is present per centimeter. Okay, in 1 centimeter how much PD, or in 1 meter how much is the PD. That is what is shown by the value potential gradient. Say for example, if it is given potential gradient is 0.2 volt per centimeter, it means what, in every centimeter there is 0.2 volts in this wire. So what is the significance of that? If you know in 1 centimeter how much is 0.2 is the potential difference, then 5 centimeter how much will be the potential difference? 5 multiplied by 0.2, that is you will get 1 volt. So any centimeters if you know that into potential gradient gives the potential difference across that particular length. That's importance. Clear? That is, if there is a length L, just multiply it with 5. This gives what? The 5 multiplied by L will give you the potential difference across the length L, small l. Okay, this is the case. Now you have to think of this is the time you have to think of the EMF E in the secondary circuit. Secondary circuit EMF E, okay, is balancing with, that means if suppose jockey is initially touched at A, there will be deflection in the galvanometer. Now if you move the jockey like this, and at one point over here when the jockey is kept in contact, you see that the galvanometer shows 0 deflection. So at that point, that is, we call it as balancing condition, balancing point. At that point, what you can equate with, what all you can equate? The EMF of the cell. Suppose this is 2 volt, the potential difference across AJ also would be 2 volt. Okay, that means this, if you write it as L, this length is what is called balancing length. So what's the main concept to understand is, at the balancing condition, the EMF of the cell in the secondary circuit should be equal to the potential difference across AJ. This is the main point about potentiometer thing, potentiometer circuit. Okay, so here therefore we can write in, since 5, if you have the value 5, then we can straight away write 5 into L. 5 into L is the PD across AJ, which you can equate with E. So E is equal to phi L. Is that point clear? E is equal to phi L, or we can say what, if we provide same current throughout the potentiometer circuit, it means what, same current is, potential gradient remains the same. So phi remains the same. If phi remains the same, we can even write the EMF of the cell in the secondary circuit is directly proportional to the balancing length. Okay, because phi is constant. So when we can write this one, if you are not disturbing the primary circuit, it's a primary circuit. So in a primary circuit, there is, we find a balancing length. At the balancing condition, the potential difference across the AJ would be equal to the EMF. Therefore, if you are keeping potential gradient constant, that is phi remaining constant, then you can write E is directly proportional to the balancing length. Actually, this is the case we are making use of to compare the EMFs of 2 cells. You must be remembering the experiment to compare the EMFs of 2 cells. There what we do, we find using one cell, normally Lagrange cell of EMF E1, you will find the balancing length, that you take it as L1. So what you will write, E1 proportional to L1. Then if it is a second cell, Daniel cell, let's say, then again you find the balancing length, that is L2. So E2 proportional to L2. So what will be E1 by E2? So then you will get E1 by E2 is equal to L1 by L2. See, this is how you do the experiment for comparing the EMFs of 2 cells. So this is how in the numerical problems the diagrams would be given, but in the experiment usually we draw the diagram this way, that is the wire like this, you will draw the wire, okay, A, B, okay, and then cell, resistor, okay, key you may connect. This is primary circuit. Okay, in the secondary circuit we will draw the cell of EMF E and cell of EMF E, yes, galvanometer and jockey. This is the balancing length. This is how you draw the diagram for the experimental purpose. Anyway, we have more to talk about potentiometer, more questions we have to discuss related to potentiometer. It's all very important questions. So I think the next class, because now it's high time to wind up the program today, and next class therefore we will be able to discuss more questions on potentiometer. So my dear students, you just keep collecting the questions related to potentiometer or anything in that matter, any question in that matter related to the current electricity or any chapter which you have done already. Collect the questions with you and wait for the next week. Monday again at 5 o'clock we will see. That time you can very well call and find out what all questions, because as I mentioned at the beginning, this is a live classroom. So you are very well able to ask your doubts. This is the program exclusively meant for you, the students of UAE. Okay, so let me wind up today's class, and next week again we will see. Okay, till then, goodbye, stay tuned.